And then later on, a second breaker bar starts forming, and a third breaker bar once you have breaking and reforming and re-breaking of the waves in the surf zone. And what we have always also got out is to have a better understanding about phase lags between hydrodynamics, sediment transport, and what elements in sediment transport do we need to include on what level of detail we need to include it to get the correct magnitude and direction of the transport. So going to what I do more today on the coastal structures and offshore structures, there's quite a few questions being asked in the design process, and these are some of them. There's run-up on rubble mound breakwaters and offshore monopile foundations, and for the foundations it's how far up can we actually put the installation or inspection platform. We need to get there, so we should have it as low as possible, but we don't want it to be torn apart by the waves, so it should also be quite high up. We have slamming loads on crest walls on top of breakwater. There could have been a concrete structure on this breakwater, and the same for monopile foundations. And a breakwater is in place to protect the water on the other side, so keep it as quiet as possible. So we want to have either waves reflected or we want to have dissipated the wave energy through the breakwater, so we have sufficiently quiet water on the other side so we can have safe loading and unloading of ships in the harbor. And then of course also stability of stone layers, both when it comes to breakwaters but also scour protection around any type of coastal and offshore structure. So slamming loads, Poulsen et al. Has been using CFD modeling to validate OpenFoam for this, so we can now confidently use the modeling. And what you can see here is that in the laboratory they created a focused wave. So they start with a couple of wave components, and at a certain location in the wave basin all these components meet and form a very high wave that will slam into the structure. And the prediction of the forces is quite good, actually very good. And what they also saw in this wave is that most of the waves don't really break. We can use simple engineering rules of thumbs, Morrison type equation, to say something about the loading, but only for these slamming events we need to actually use the CFD model. So they also studied how can we optimize computational resources or use of computational resources to get as good a design as possible without using excessive amount of CFD time. So permeable coastal structures, as I said, reflection, transmission and dissipation of waves, wave energy are key questions. Overtopping is a phenomenon like that. You don't really want to have structures on the other side. You don't know how big couples there can actually be in this tongue of water flowing over into a structure on the lee side, so they can create quite a lot of damage. And then also forces on a structure like that and global stability of the structure. And what I will present for you now is results for reflection, dissipation and overtopping. So these results come from a simplified breakwater layout that we had studied for research purposes at Deltares. And you can see here how the experimental values versus simulation for reflection coefficient is essentially within plus minus 10%. That's the lines, but the points are even closer to the one-to-one fit. We are working with a dissipation coefficient, which is a factor in an exponential decay, and also that is captured very nicely with the numerical model compared to the experimental values we have. And finally, the surface elevation in front, we model that for irregular waves, and you can see how the measurement for the wave height through the structure as well is essentially on top of the measurements. So we've come quite a long way to use this type of modeling to say quantitative things about a given design and not qualitatively alone. When it comes to overtopping, a colleague of mine from university have looked at overtopping rates on coastal structures and studied it for 2 designs alone, but the scatter within the numerical result is essentially equal to the scatter of the experimental results. So we're quite happy with the results, but a small disclaimer, I would like to see more research, more comparison also against perhaps more complex designs of a breakwater or a vertical seawall and the like. So now coming to the more exciting part. So the 2 pieces I've been going through now has been done several times in the past. I mostly focused on my own work because I can tell clearly about that. But the branching of both sediment transport and coastal structures is quite new, if not unique. So I'm very happy to be able to present that here today. And the study starts with what we call an open filter. There's a growing interest in trying to keep designs as low cost as possible and to push the limits of given design rules. So how thin can you make a stone layer on top of a sand core is the base question, such that we still have it be stable or structurally the integrity of the structure will remain over the next 50 years. So it's a study about how the sand moves inside the structure under wave loading. And what I showed you with the Exner equation, sand come in, sand go out, and there's a change. Suddenly here we have an additional complexity because sand goes in, sand goes out. But the question is, am I eroding down to a pure sand bed? Then we have the classical problem. But if we are putting sand into between the pores of the stones, we need to make sure that we only fill the pores, because we cannot put sediment where there already is a stone. So it adds a complexity to the morphological modeling and include that. So it's these questions about how much we can save in terms of a design is something we are currently working on together with our industry partners. So that's Boskalis, Van Oort, and Royal Haskoning, all Dutch companies. So we can make one step further. But we don't even know how sediment moves in between the stones. I looked through the literature and we found a few experimental campaigns back in the 80s, and that was essentially it. And then we had these quite complex experiments from a recent campaign that we undertook at Deltares. So we knew how the reshaping of the profile looked like after 6 to 12 hours of wave exposure. But that was essentially it. So we took a bit of the one experimental campaign and got to know something about the transport shape, and then we just put it into our full numerical model and saw how well do we predict the changing shape. And in that way, essentially, with a numerical model, came up with a sediment transport model for transport within a filter layer. And so we calibrated against a range of tests, and we got quite a good comparison between the set we were calibrating on and the numerical model, which was fortunate, but we also needed to validate it. So we had reserved a couple of laboratory tests for that purpose. We plug it in, and we get a comparison like this. Data will be the change in bed level over the entire slope of the open filter, and the model will then be the numerical results. So we do quite all right. Of course, there's room for improvement. But what we also saw was that the deposited sediment inside the filter layer did not deposit with the same porosity as it was eroded with. So there was a gradual compaction of the sediment over time, meaning that if the wave loading had continued on this very large deposition, maybe we would actually have been seeing a smaller deposited area, even though we didn't remove any sand. It was just compacting over time. And an effect like that we have not included in the numerical model. So we do need more data to say something about sediment transport inside filters, but we are confident enough that we can start looking at complex configurations and at least qualitatively and to some degree quantitatively say something about what is the effect of changing the slope, how can we lower the amount of erosion underneath the stone layer and in that way optimize it. Or do we need geotextile on part of the slope and we can leave the slope without geotextile on another part, preferably that part that is always wetted because it's hard to install geotextile below water. So how can we optimize installation process, design, and the lifetime of the structure? So finally, outlook. I haven't talked about computational times, and when we are running a full 1,000 waves, irregular waves, it will take around a week or so. So there are substantial computational time or computational resources required. So that is a bottleneck, and hopefully we'll be able to progress on that and push the models even further. But I would still say that detailed CFD modeling is a good and an accessible research tool and design tool to be used in many fields of engineering. And I've even seen people start put vegetation in below waves so they can see how is the vegetation moving, how is the wave damping, and what happens in between the vegetation. It could be resuspension of sediment, moving nutrition around, understanding why is a vegetation field only as big as it is. So, and then when it comes to sediment transport and morphology, it's something that will always come up. What we have empirical formula are quite often just based on pure steady current relationships, and we say, yeah, we just apply it to accelerated motion such as waves. But we still have to see whether that actually holds when we go into the amount of detail that we are pushing the models into. I would like to see more validation. There has been done some validation against coastal profile development with this type of modeling, but still limited. So to get full confidence, it's nice to expand on these type of things. Nonetheless, I'll start with the end with the positive. We do gain a lot of understanding of both coastal structures and coastal morphodynamics by applying these models. For instance, the Ripple movie I showed you, we can start understanding how are they migrating. The initial stability is short, which is also looked at by stability theory, but how do they then become the size they are? And we can see how they merge, become larger, migrate, and how important the intra-wave motion of the morphology is. So we can start understanding at a more detailed level things that might simply not be possible to measure in the lab because we need to put an instrument where we want to measure. And that's often a restriction, so at least we can help understand measurements by looking at the CFD models and have a sort of parallel track on the research. Thank you.